The following is a quick overview of the Millrock technology micro-freeze dryer with LyoSim and LyoPAT. The micro-freeze dryer is a small batch protocol development freeze dryer that uses anywhere from 3 to 37 vials to produce fully transferable protocols. The system has a built-in process analytical technology that allows you to collect all the critical process parameter information and use that information for determining the best protocol to develop. The LyoSim ring is a ring that's mounted in the system that will track the product temperature. You can use the system to track the product temperature to create center vials or to create edge vials. A heat flux sensor is mounted on the shelf, which provides constant direct measurement of the heat flow going into the vials. And using this information, we can get the mass flow, cake resistance, and some other critical process parameters. This is done continuously, unlike other methods, and it's done with a direct measurement as opposed to calculations. Here's the LyoSim ring filled with vials. These are partially stoppered vials with thermocouples in place. Give you an idea of what it looks like. It also has a stop ring system here that at the end of the run can stopper the vials in place. The objective of the use of the micro-freeze dryer is to develop a robust transferable protocol. The system will determine the optimized product thermal history, provide that information to you, and you can use that for transfer to production. The critical process parameters that the system develops are heat flow, mass flow, thermal conductivity of the vial, kV, cake resistance, RP, and several other parameters that you can determine what's going on during the cycle. One of the unique things about this system is that we have the ability to actually monitor and control the freezing process unlike any other technology available. Typical use of this system is you start in an analyze mode. In analyze mode, you would typically use a recipe, an existing recipe that's standardized, and do a complete run, which will give you a baseline the baseline thermal history of what's going on. It'll tell you how much heat's coming from the shelf, how much heat's coming from other places. It'll determine the kV of the vial in that under that scenario, and all the other critical process parameters. So you create a baseline to know where you are, and then you can start optimizing the cycle. In the optimize mode, you have several different options that you can change the different freezing methods. You can use a recipe, you can add annealing, you can add controlled nucleation, and you can add controlled nucleation with a heat flow control after nucleation. Important for everybody to understand that controlled nucleation only nucleates about 10% of the available water. 90% of the freezing takes place after the nucleation event, so it's very important to control and at least to be able to monitor that process. In primary drying, we have a technique called auto dry, which will control the product temperature at some point near or below the critical temperature. It's a closed loop system, so it'll control the shelf temperature based on the product temperature and optimize the cycle for you. You can use any combination of these to determine the best methodology for improving your protocol. Once you have that information, you can use the critical process parameters and kV to actually transfer the protocol, and we'll show later that you can actually use the LyoSim ring to actually simulate larger systems as well. This is a data screen here, just to give you an idea of some of the data that comes out. So here's an example for a freezing cycle. We have the blue line as the shelf temperature. We can see that we stabilized at 5 degrees and minus 10 degrees, and then pulled down to minus 40. The resulting product temperature is the green line here. And this red line is the heat flow. We're actually measuring the heat flow that's going into the vial. And for example, here you can see the heat flow went up to approximately 0, which means we stabilized at minus 5, and all the product was now at minus 5 and stable. And we can tell that by looking at the heat flow. We just don't have to base this on time or temperature. We then reduce the shelf temperature to minus 10. We can see the heat flow change. And then we have these two significant events here. We actually had nucleation events that took place when we were holding here. You can see that with the temperature also, but not as clearly. As we reduce ramp the shelf temperature down to minus 40, you can see the heat flow changed in this V pattern pretty dramatically. That means that during this process, the heat flow is changing as the ice crystal forms, and the ice crystals are not being uniformly created. We can see nucleation events here. Oops, sorry about that. We have 3 nucleation events here, here, and here. So this V pattern is actually something we don't want to see during freezing. If we use our other technologies, in this case we used controlled nucleation and controlled heat flow, we see that we bring the shelf temperature down to -5, product temperature came down, stabilized, and we did a controlled nucleation event here. You can see one single nucleation event that took place, and then controlled the heat flow at a specific level by adjusting the shelf temperature to keep the heat flow constant. You can see the product temperature dropping here. This profile will give us uniform crystal growth inside the vial as well as across the batch. So that the control nucleation gives us uniform crystals across the batch as to start, and then the heat flow control gives us uniform heat flow into the vials, and then therefore uniform crystal growth. We overlay these two, we can see although the shelf temperatures don't look too dramatically different, the heat flow going into the product is dramatically different, and we'll see the effect that this will have on primary drying. So if you take a look at primary drying, here's the heat flow, the product temperature, and the shelf temperature during the analyze mode. During analyze mode, with our standard protocol, it took over 2,000 minutes for primary drying. We got a KV of about 20.7, an RP of 3.13. With a -25 inlet and a -35 product temperature. We then did the controlled nucleation and controlled heat flow, and then put auto dry into effect. And here's the primary drying cycle that we get after that. We reduced the primary drying cycle almost in half, and KV dropped by about 15%. I'm sorry, 20, 30, let's see here, by 3. 15%, yep. And RP reduced pretty dramatically. Now, our shelf temperature was able to run it much higher using closed loop control and auto dry. And the product temperature remained about the same. So our heat flow is much higher than it was before. And the result is a much shorter drying time. And we can see that this precipitous drop here in heat flow at the end of the cycle is telling us that we have very uniform crystal structure across the batch and inside the vials. In the analyze mode, our heat flow came down very slowly. You'd see the same thing with the Pirani, for example. This tells us that we don't have very good crystal structure that was formed during freezing. So the freezing method that we chose gave us much better heat flow, much shorter primary drying time, much better control over the product temperature. We can look at the mass flow. This is the mass flow for the analyze cycle. And then for the optimized cycle, much higher heat flow during the process, much shorter primary drying time. If we take a look at the cake resistance and compare the two, during the analyze mode, this is what the cake resistance looked like. And during the optimized mode, we can see that the cake resistance dropped pretty dramatically. And this is what's giving us the ability to run at a much higher shelf temperature. Gives us a much more robust protocol as well, because we're controlling the product temperature much better, even with a higher heat flow. Once you've collected all this data, there are several methods of transfer. Today, most people just use an extended primary drying cycle, where they extend the cycle for about 30% longer. This is due to the lower KVs in production systems and lower thermal conductivity to the vials. In addition, there's typically a lower supercooling effect because there's less particles during the freezing process, so the crystal structure is not really as amenable to the primary drying cycle. Another way we can use this data is we can take the KV for the target system compared to the KV for the source system being the microfreeze dryer, and calculate the temperature of the shelf in the target system being a production or a pilot system. This has been demonstrated to work very well, and other videos will demonstrate this. Recent development is one major pharmaceutical company has used the system where they've adjusted the LyoSim ring to a much lower temperature than the product temperature, been able to actually simulate larger systems such as a production system, and actually simulate how the product would dry in a production system. This is kind of unique and novel, obviously, if we can actually just simulate a larger system rather than doing calculations. New feature that's being added to the system is a glove box with a HEPA filter. This it will simulate a production environment, which will reduce the amount of particles in the processing area, enabling a lower supercooling event, so we can actually simulate more of the production environment and give you a much better, a much closer simulation of production systems. Thank you for your time. We look forward to hearing from you if you have any more interest. And certainly, please stay tuned for more videos on the micro freeze dryer and the technologies involved.